Have you ever stopped and wondered how a computer can learn to recognize your face, or understand what you're saying, or even drive a car all by itself? It kind of feels like magic, right? Well, the secret isn't magic at all. It's actually inspired by you, by the human brain. Today, we're going to peek behind the curtain of artificial intelligence. So that's the big question, isn't it? How do you actually teach a machine to think, to make decisions? I mean, where would you even start? Well, as it turns out, the answer was right inside our own heads the entire time. Says scientists looked at the most powerful computer on the planet, the human brain. Our brains are just packed with billions of these tiny, specialized cells called neurons. They're constantly firing signals to each other, and that's how we learn, how we remember, how we make sense of everything. The pioneers of AI had this amazing thought. Hey, what if we could build a version of that inside a computer? And that is exactly what they did. They created the artificial neuron. The best way to think of it is like a single microscopic brain cell, but for a computer. This little guy is the fundamental building block for pretty much all modern AI. Okay, now this is where it gets really, really cool. To truly get a feel for what an artificial neuron does, we're not just going to talk about it. We're going to build one right here, right now, piece by piece. You ready? Let's jump in. Here it is. This is our blueprints. Believe it or not, every single artificial neuron, no matter how complex the AI system is built from these 5 main parts. They all work together in order to take in some information and then spit out a decision. So let's break them down one by one. First up, we have the inputs. A neuron can't do anything without information to work with, right? And that's all inputs are, the data you give it. So if an AI is trying to identify a picture of a cat, the inputs might be all the little pixels that make up the image. If it's listening to a song, the sound waves are the input. It can even be just plain old numbers. But here's the catch. Not all information is created equal. The neuron needs to know what's important and what's not. And that's where weights come in. Weights are basically just numbers that act like an importance score for each input. For example, if we're looking for that cat, the input for has pointy ears is going to get a really high weight. But the input for is on a blue background? Not so important. That'll get a very low weight. Okay, our third ingredient is a little something called bias. Now, this one can sound a bit tricky, but honestly, just think of it as a helpful little nudge. It's a fixed number that gets added to the total, just to make the neuron a little more flexible and help it find the right answer. Let me give you a super simple analogy to make this crystal clear. Imagine a student needs to get 50 marks on a test to pass, but they were sick that day and just didn't do their best. So to be fair, the school decides to give every student 5 extra marks, just a little boost. That plus 5, that's the bias. It's a constant push that helps the neuron make the correct decision by adjusting the final result just a tiny bit. All right, so let's do a quick recap. Our neuron has received its inputs, it's multiplied them by their weights, and it's added that helpful bias. Now it's sitting there with a final number. But so what? What does it do with that number? It has to make a decision, and for that, it has its very own on/off switch. This switch is called the activation function. Its job is simple but absolutely crucial. It looks at the final calculated score and decides if that score is high enough to matter. If it is, the neuron activates. We say it fires, and it sends a signal forward, on. If the score is too low, it just stays quiet, off. And what's really cool is the switch can have different personalities depending on the job. A threshold function is a simple pass or fail decider. A sigmoid function is a bit more nuanced. It won't just say yes or no, it'll give you a probability, something like an 85% chance this is a cat. And then you've got something called ReLU, which is interesting. It only pays attention to strong positive signals and just totally ignores everything else. And all of that brings us to our fifth and final part, the output. After that activation function makes its choice, the result gets sent out. This is the neuron's final answer. It's one decision. Yes, this is a cat, or no, this isn't. All right, theory is great and all, but let's see our new neuron in action. It's time to put all 5 pieces together and use our artificial neuron to do something practical, like calculate a student's final grade. Okay, let's walk through this together. Our inputs are the student's marks, an 8 in science, a 7 in math, and a 6 in computer. Next, we apply the weights. We'll say science is a little more important here. We'll add a bias of +1, maybe for good attendance. Then we do the math. And finally, our activation function has one rule. If the total score is over 5, the student gets an excellent. So here's where it all comes together. We take the science mark, 8, and multiply it by its weight, 0.4. We do the same for math and computer. We add those all up, and then we add our bias of +1. The final score is 8.1. And now for the final step. The activation function checks the score. Is 8.1 greater than 5? Yes, it is. So the neuron fires, and the final output is excellent. See, our little neuron correctly processed all that information and made a decision. And here you can see that whole process laid out visually. It follows the exact flow we just built, from the inputs, through the weights and the bias, to the final calculation and the big decision. We went from just a few simple numbers to a final, meaningful result. So we did it. We successfully built a working artificial neuron. Now, it might just seem like a bunch of simple math, but when you zoom out, you start to see a really, really powerful idea about how AI actually learns anything at all. It really all comes down to this. AI isn't magic, it's a process. And for an AI, working harder just means constantly adjusting those weights and biases over and over again through thousands of examples. It gets a little bit smarter with each try until its outputs are right. It literally learns from its mistakes, just like we do. And that leaves us with a final thought to chew on. We just looked at one single artificial neuron. It's pretty simple, but it's effective. And when you realize that this tiny engine is what allows an AI to recognize a face or understand your voice, it kind of makes you wonder, if just one of these can do all this, what do you think millions or even billions of them all working together in a vast network can achieve?